also very happy to see many of my old friends in these fields. And now I belong to the Institute for Nanoscience Design, Osaka University. This institute serves the program for graduate students and also the young people working in industries about the science and technology of nanofields. And also, as someone said before, the application of nanomaterials. Sometimes people is worrying about the hazard of the materials. And so we want to develop the so-called public engagement for these technologies. And the students should know somewhat about this kind of issues. And after they get the job in some companies and some institute, they should continue to think about this kind of public engagement. And that will be the best way to develop the newly emerging science and technologies in societies. And now I want to talk about these items. This is the outline. The first, I will talk about the copper ion heavily doped sodium chloride. What would happen? And inhomogeneous broadening of exciton bands, and then size-dependent properties of confined excitons, and also the optical nonlinearity, lasing, and superfluorescence, and optical manipulation of floating quantum dots. The last two topics are done recently. And first, copper ion heavily doped sodium chloride. That is the old history, and the discovery of quantum size effect on excitons. But this discovery is not the first discovery, but Efros and Ekimov has already found such kind of phenomena in the same materials. And as you know, the light comes into the semiconductors with more than band gap energy. Then the electron is excited in conduction band and the hole remains in the valence band. And through the Coulomb interaction, they form the excitons like this. And so the exciton has the internal motion between electron and holes, and also the translational motion of two particles together. And this is the schematic diagram of the band gap energy band structure of cuprous chloride. And because of the negative spin of its splitting in the valence band, we have a very simple exciton structures. One valence band, one conduction band. And so the simple exciton is formed. And but the band gap energy is about 3.2 electron volt at 4.2 Kelvin. And so just in the ultraviolet limit. And also the translational mass of exciton is rather heavy, 2.3 multiplied by the mass in vacuum. And so this very strong Coulomb interaction is realized in this material. And the so-called exciton Bohr radius is only 0.7 nanometer, a very compact exciton, and having the binding energy about 200 millielectron volt. So it is quite stable even at elevated temperatures. And now I will talk about the copper ion heavily doped sodium chloride. So there were two papers in 1957 by Gross and Kapliansky, and also 1965 by Ueta and other people. And they, in their paper, they suggested the precipitation of cuprous chloride colloidal particles in solid matrix of sodium chloride. The result of the Ueta's group is like this. And this is the absorption spectrum. And this is the bulk exciton energy. And a little bit high energy side, we found Z3 exciton and also the Z12 exciton. They are separated by the spin orbit splitting of the valence band. But the energy is somewhat blue shifted, and also the line width is rather broad. And also they found some fine structure inside the lowest exciton bands. And they could not explain the reason why. So they have no idea about the quantum size effect. And in 1983, Professor Ueta, on his retirement, entrusted me with this unsolved problem. And I started work with my graduate students. And his name is Kirihara, not Harakiri, but he's Kirihara. And he measured the excitation spectrum of the luminescence and found the very important things. And this is the results. The excitons in cuprous chloride microcrystals embedded in sodium chloride. And I presented this paper in poster sessions in the International Conference of Luminescence in 1984, which was held in Madison in the United States. And the result is as follows. We have an absorption spectrum, somewhat broadened and shifted to high energy side, and also the very strong luminescence for lowest exciton state. And we have a bulk luminescence band here, and so somewhat shifted to high energy side. And then we excite the sample with monochromatic light inside this absorption band. Then we could get such kind of result. And we see some fine structures which appears in broad luminescence band. And when we shift when the excitation energy goes to low energy side, these structures also goes down. And the separation between them becomes smaller and smaller and almost converges into the bulk exciton energy. And so we've thought that the inhomogeneous broadening is caused by the size distribution of microcrystals through quantum size effect on exciton energy. And this is the proceedings, the cover of this International Conference of Luminescence. And at the poster session, Professor Kapliansky from Yoffe Institute came to my poster and gave me his paper in 1957 I just introduced, and also introduced me the very new work on cuprous chloride microcrystals in glass matrix studied by Alexei Ekipov and Onuschenko. And it was published in the Translation of Soviet Physics in 1982. And this was the result. And by changing the average size of nanocrystals from 7.5 nanometer to 2.5 nanometer, then the peak energy of the exciton absorption band shift to high energy side. That is truly the quantum size effect. And the interpretation was done with the help of Sasha Efros and also his brother Efros. And so depending on the exciton Bohr radius relative to nanocrystal radius, and if the exciton Bohr radius is larger than the nanocrystal radius, so-called strong confinement or electron hole individual confinement is realized. And in that case, the energy shift is expressed by the inverse of the reduced mass of exciton. And that's the case for gallium arsenide. The Bohr radius is 14 nanometer. And so if we have nanocrystals with the radius of a few nanometer, then this situation is realized. But in case of exciton Bohr radius smaller than the nanocrystal radius, then weak confinement is realized, so-called exciton confinement. In that case, the exciton translational motion is confined inside nanocrystals. And so the energy shift is expressed by inversely proportional to the mass of translation, the translational mass. And that's the case for cuprous colloid because the radius is very small. And as you see that the wave function of the translational motion of exciton is fully coherent all over the quantum dots. And so the extonic wave is fully coherent. That's quite important I will explain later on. And, but at the same conference, there was an invited talk and on the development of bulk optical properties in small semiconductor crystallites presented by Louis Bruce. And that's, the semiconductor was produced through the colloidal method. And I have a very short knowledge about the chemical reaction. And so I thought from the physics side, we thought that in order to make the very pure samples, we need a very pure chemical source in order to get the very pure semiconductors, nanocrystals. But in case of colloidal nanoparticles, they used some chemical agent having the purity of 99.9% or something like that, which is rather dirty with the sense of physics, physicist. But even with using such kind of chemical materials, they can make very pure quantum dots. That was quite surprising for me. But anyway, it was quite successful. And I was very much impressed by his work. And if the average size of nanocrystals is 3 nanometer, and the energy is somewhat shifted from the nanocrystals having the radius more than 10 nanometer. And so we have some blue shift when we go to the smaller crystal size. And as already Louis explained, and so from atom to cluster and crystal. So that's the real fusion between chemistry and physics. And this work, from this work, I decided to continue my nanocrystal study. And this was a picture taken with Louis. And at the top of the building called World Trading Center. No, it doesn't. And next one is the inhomogeneous broadening of exciton bands, the discovery of size-selective excitation method. So if the some luminescence or absorption band is inhomogeneously broadened, then with using the very narrow laser light, which situated inside this inhomogeneously broadened absorption band, we can see the so-called site-selective excitation, or so-called hole burning effect can appear. And first, I will explain briefly the sample preparation. With using the transverse Bridgman method, we make the sodium chloride single crystals. And this sodium chloride is heavily doped with copper ions. And then the single crystal is formed. And with using the annealing method, we can control the average size. Of course, the distribution of the size is rather large. But when we anneal at low temperature, the large crystals are formed. And with high temperature annealing, we can make a small cuprous chloride. And the typical characteristics is as follows: copper chloride nanocrystals and sodium chloride single crystal matrix. And nominal concentration is about 1 mole%. And average radius is, by size control, from 2 to 7 nanometer, and so on. And we use the sodium chloride single crystal matrix. And so it can easily cleave into a thin platelet, for example, 0.5 millimeter or so for the sample. And this is the transmission electron microscope image. And the black one is the sodium copper chloride nanocrystals. And we have nanocrystals having the few nanometers in radius. And the nanocrystal concentration is about 10 to 16 per cubic centimeter. And so about 100 nanocrystals exist inside the volume of a cube of 260 nanometer. 260 nanometer is corresponding to the effective wavelength at the extern resonance. And so when we excite the sample with the resonance, extern resonance energy, then within the wavelength, one wavelength, we can excite about 100 nanocrystals at the same time. So so-called ensemble phenomena becomes important. And then we took the excitation spectrum. That means inside the broadened absorption luminescence band, we fix the observation energy and take the excitation spectrum. And then, for example, if we put the observation energy at the high energy side of the extern band, then we have several structures appearing in high energy side. And the excitation spectrum gives some indication about the absorption band, which is located on the high energy side of the lowest extern band. So this result shows us that there are many isolated states that exist on high energy side of the lowest extern band. And when we change the observation energy to low energy side, then these structures converge into the bulk Z3 extern band or Z12 extern band, and like this. And so size-selective observation can be possible. So this broadening has come from the inhomogeneous broadening due to the wide size distribution. And so when we observe the high energy point of the luminescence band, then we are looking at the nanocrystals having smaller crystal size. And when we observe at the low energy side of the luminescence band, then we are looking at the larger crystal. So size-selective observation becomes possible. And then with using this method, we can analyze the splitting of the extern energy like this. This is the luminescence energy, and this is the excitation energy. So we have many levels split. When we look at the smaller crystal size, the separation becomes bigger and bigger. And with using the so-called size quantized wave vectors, which was introduced by Lewis already, and then we should see some structures at these points. And the result is something like this. Of course, the agreement is not so beautiful, but anyway, we can say that this structure comes from the lowest extern. And for example, this one comes from the second excited state of the lowest extern. And the red line shows you the structure coming from the second extern band, so-called Z12. And then we can do the size-selective excitation. That means size-selective observation. So we can observe the size-dependent properties of confined extons, even though we have a very wide size distribution in one sample. And successful, and these work were done mostly with the successful international collaboration I will explain now. And here is Sasha and Alexei and me in 20th International Conference on the Physics of Semiconductor, which was held in Thessaloniki, Greece in 1990. I met for the first time with them and started the collaboration. And also, I have to introduce Catherine Goudon, who belongs to the Institute of Nanoscience in Paris. And he's also the good collaborator with me. And the first work was done with the collaboration with Catherine, and the size-dependent radiative decay time of confined excitons in cuprous chloride microcrystals. So nanocrystals size versus exciton radiative decay time. And if the crystal size is smaller than the mean free path. Mean free path is if the exciton is formed and moves around inside the crystal and collide with phonon and so on, then the mean free path is fixed. But if the mean free path is larger than the crystal size, then the translational motion is fully coherent inside the 1 nanocrystal. And so then the emergence of intrinsic properties of coherent exciton without dephasing. So this intrinsic property means with the increase of the size of nanocrystals, then the radiative decay rate becomes also increased. And so-called exciton superradiance can be realized. And these are the results. And I will don't touch with in details. But anyway, the luminescence coming from the isolated quantum dot and also the luminescence coming from the quantum dot ensembles, we can calculate the radiative decay time, and which is dependent on the effective radius of nanocrystals. And for abscissor, we plot the energy shift, which is inversely proportional to the square of the size. And you see that when the crystal size is smaller than 5 or 6 nanometer, then the experimental points sits on the straight line. And we plotted this point with a logarithmic scale. And so that means this dependence shows you that the radiative decay time is inversely proportional to the volume of nanocrystals. And the exciton coherence is all established all over 1 nanocrystals, and collective oscillator strength of all cuprous chloride molecules in the nanocrystals. Then superradiance is realized. And for example, for 7 nanometer nanocrystal, then the radiative decay time of exciton is only 80 picosecond or so, which is much, much smaller than the radiative decay time of a bulk exciton. And this kind of phenomena was already found in molecular assemblies in some researchers in Netherlands in 1988. And our findings was in 1989. And this one is, this picture was taken in 1991. And when I was invited by Louis to attend the Gordon Research Conference. And the title is Metal and Semiconductor Clusters. And here I am, and here the Bruce is here. And so at this, in this conference, we could discuss together with chemists and physicists, not so many biologists, But anyway, we could shake hands the two fields of chemistry and physics together on the common subject of nanocrystals. And the second work was done with the collaboration with Catherine and also Alexei. That was the effect of matrices on nanocrystal shape. And when we measured the two samples, one is in glass matrix, and the other one is in sodium chloride matrix. In case of glass matrix, the absorption band is very smooth, and also the shape of the nanocrystal is almost spherical. But in sodium chloride matrix, we see some oscillatory fine structures inside. And then we assume that cuprous chloride cubes with the discrete size is epitaxially grown by steps of half the lattice constant of 0.54 nanometer. And then the calculated external energy should appear at these energy positions, and depending on the multiple integer of half the lattice constant. And this was the assumption, and but we could reproduce the peak energy with using this assumption. But later on, we could find that in sodium chloride matrix, really the cube shape was found in transmission electron microscope. And then this work was also introduced in some luminescence conference. And then Professor Friedrich in Dortmund University in Germany promised me to measure the determination of the orientation of cuprous chloride nanocrystals in the sodium chloride matrix with using his two-photon absorption method for creating the exciton. And polarization selection rule for two-photon absorption for creating one exciton, then it is dependent on the crystal axis. And when he excites the sample with using the linear polarization parallel to the sodium chloride crystal with 110 direction, then we could see the very beautiful structure of excitons. But when he changed the orientation of the polarization of the excitation laser light to 100 direction, then almost the exciton structure disappears. And this is the indication that this kind of selection can be applied to the zinc blende materials. And the cuprous chloride cubes are epitaxially grown, and with the axis is aligned to the sodium chloride crystal axis. And then also it's rather difficult to see, but you see that the cubic shape of the nanocrystals is really formed inside the sodium chloride matrix. And the third work was done with the collaboration with Alexei, Catherine, and also Sasha. And this was the polaron and exciton phonon complexes in cuprous chloride nanocrystals. It's the interaction between exciton and optical phonons. And so we see excitonic polaron and also exciton phonon complexes, and 1p state hybridized with these exciton phonon complexes. I do not explain in details, but anyway, the optical forbidden 1p state becomes allowed as a result of the formation of hybrid exciton phonon complexes with angular momentum equal to 1. And, and also in 1995, on the occasion of about the 10 years of colloidal nanocrystals, Louis, Sasha, and I started to edit a special issue entitled Spectroscopy of Isolated and Assembled Semiconductor Nanocrystals. Just the chairman shows you the book. And a special issue of 484 pages with 37 papers was published in 1996. And I will introduce two works, which is not my work, but an exciting report which opened different utilization of quantum dots. One is the cadmium selenide single quantum dot microspectroscopy. Munji already explained you this morning, and random telegraph signals, and it's a blinking of quantum dots. And I think that it's the first visualization of photocatalytic reaction, oxidation, and reduction can be seen just at this sudden change of the fluorescence intensity. And another work is the semiconductor nanocrystals as fluorescence biological labeling. And that was done by Simon Weiss and also Pauls. And this pictures. And it was quite surprising for me that the quantum dot is already commercially sold for this biological labeling purpose. And now I go back to our recent work on optical nonlinearity, raising, and superfluorescence. And that's the collective phenomena caused by quantum dot assemble. And as you know, that if we have two excitons and collide each other, then form the biexciton, like a hydrogen atom forms the hydrogen molecule. And optical formation of biexciton, we have two kinds of method. One is the indirect formation through one photon excitation. So, for example, band-to-band excitation or resonant excitation of excitons. Then after that, the exciton-exciton collision occurs and form the biexciton. And the other one is the direct formation of biexciton through two-photon resonant excitation. And so the biexciton energy is double the exciton energy minus the binding energy of biexciton. And so with using the laser light, energy with the energy, which is a little bit less than the exciton resonance energy, then by two-photon excitation, we can directly form the biexciton. And then the luminescence comes out from the biexciton state to the exciton state. And in case of quantum dots, we could also see such kind of phenomena. And when we excite the sample well inside the exciton absorption band, then with strong laser light, then we see not only the exciton luminescence, but also on the low energy side, we see the so-called biexciton luminescence. And when the excitation energy shifts to the low energy side of the absorption, there exists almost no absorption of exciton. But with strong excitation, we still see the biexciton luminescence. And with changing the excitation power, we see the nonlinearly grow this biexciton band, which indicates really the biexciton luminescence. And biexciton luminescence band are still observed with excitation photon energy below the one photon excitation absorption band. And so the two photon direct absorption corresponding to biexciton creation is rarely occur. And then when we increase the excitation power for two photon absorption of biexciton creation, then the laser action starts. And this is the cavity mode. And as you see that with this one is excitation laser light. And perpendicular to the surface of the sample, we see the laser emission. And laser emission appears a little bit higher on the side of the normal biexciton luminescence. And no lasing occurs with circularly polarized pump light. There is a polarization selection rule for two-photon absorption. When we use the circularly polarized light, if the polarization direction is the same, then we have to excite the biexciton state, which has the angular momentum J equal 2. But in our case, the lowest biexciton energy, biexciton is formed by the angular momentum J equals 0. So we need the counter rotating two excitation light in order to do such kind of two-photon excitation. So with using the linearly polarized light, we have a left-hand circularly and right-hand circularized light at the same time. And so only for linearly polarized light, we can excite this kind of lasing. And that is the another indication that these ones are coming from the biexciton luminescence. And the most important thing is the mode distance and emitting direction. From the mode distance and emitting direction, the cleaved surface of the sodium chloride acts as a cavity. But as you note, that the reflectivity is only 4 or 5%. So it's a very poor cavity, but still we have a very efficient lasing. And another thing, important thing is that of course, with using the one-photon strong excitation inside the exciton band, we also have some lasing. But suddenly, the intensity goes down within a few 10 seconds or so. But for two-photon excitation, directly creation of biexciton, then it's quite stable. And the so-called photofatigue effect is very important under one-photon excitation due to the OGA ionization process, but not much serious under direct two-photon excitation. And also another thing is the threshold of lasing. When we use the pulsed excitation with the pulse width of 2 picoseconds, then the threshold for laser action is about 100 microjoule per square centimeter. But with using the 200 femtosecond laser light, the threshold energy is 1 order of magnitude smaller. This is the good indication that it's ultra-fast lasing process. And in order to explain this mechanism, we introduced the so-called superfluorescence of nanocrystals. Ensemble of mesoscopic dipole of n times of nanocrystals coherently excited, and also the population inversion at the initial stage of excitation, and then so-called decay superradiance is realized, and the coherent electromagnetic coupling induces a macroscopic dipole, and such kind of pulse shape luminescence comes out. And this is the result, and we have the pulse-like luminescence comes out only just after the excitation, and this has this kind of shape. And so we think that the lasing is coming from the so-called superfluorescence mechanism. And maybe the time is almost over, and okay. So then I will shortly explain the manipulation of using excitonic resonance. And this is the theoretical proposal. And when you excite the nanocrystals with non-resonant energy or resonant energy, you can push the samples with so-called photon pressure. But with using the resonance energy, then even at the crystal size of a few tens of nanometer, we see very strong acceleration can be realized. And then this is a schematic diagram of optical manipulation. Inside the superfluid helium, we use the aberration laser to make the small nanocrystals inside the liquid helium. And then we shine another manipulation laser and transfer the nanocrystals to the silicon substrate. And the result is something like that. Without laser ablation, manipulation, we have a very wide size distribution. But with using the femtosecond laser manipulation, the size distribution becomes narrow. And also, when we use the picosecond laser light and having the narrow bandwidth, then the distribution becomes much narrower. And so that means we can make the size selective manipulation. So thank you very much for your attention.